my name is Giadda Hernandez, and this is my independent study presentation on nuclear chemistry. So these are the topics that we will be discussing today, which include applications, types of radioactivity, value of stability, equations, fission and fusion, kinetics of radioactive decay, and some interesting facts. Firstly, I will be talking about applications, and there are several types of applications, but the two that I wanted to focus on for this presentation are nuclear power and radiation therapy. So essentially, nuclear power is when nuclear reactors are utilized. They utilize controlled fission reactions to generate electricity. And this is very beneficial to us as humans as it helps us create a low carbon footprint. And unlike fossil fuels, these nuclear power produces electricity with minimal greenhouse gas emissions. And so for radiation therapy, this is specifically used towards cancer treatments, as control radiation is directed at cancer cells to destroy or inhibit their growth. And you can also tailor this kind of radiation therapy based on the specific characteristics of a patient's cancer. Next, there are 4 different types of radioactivity, and this includes alpha decay, beta decay, gamma ray emission, and positron emission. So for alpha decay, essentially the emission of a particle compromising 2 protons and 2 neutrons from an unstable nucleus. And it's characterized by low penetrating power due to the particle's substantial size, and it exhibits high ionizing power. So for beta decay, this process involves the expulsion of an electron from an unstable nucleus. In certain instances, a neutron undergoes transformation into a proton, subsequently giving rise to an electron. And this is distinguished by high penetrating power, making it smaller in comparison to the alpha particles. And it exhibits a low ionizing power, unlike the alpha decay. For gamma ray emission, this is a type of electromagnetic emission with the shortest wavelength and highest energy. And this possesses the highest penetrating power, but demonstrates low ionizing power. And it's frequently emitted in conjunction with other decay types, leading to its emission in equations. Lastly, positron emission. In this decay type, an unstable nucleus releases a positron, the antiparticle of the electron. So this shares the same mass but possesses an opposite charge. And I've also added an image right here showing the symbols for alpha, beta, and gamma and their corresponding equations. And here is a checking for understanding. Please pause. Next, we'll be discussing the value of stability. So the evaluation of nuclear stability is significantly influenced by neutron to proton ratio. An overly high ratio points to an excess of neutrons steering towards beta decay. But on the contrary, an excessively low ratio hints at a surplus of protons, triggering positron emission. So a balanced ratio of 1:1 indicates stability, often referred to as the valley of stability. An abundance of neutrons in the ratio corresponds to deviations from this stable valley. And I've added a photograph right here to show what this might look like in the classroom as a question on a graph. And next there is a checking for understanding, so please pause if you would like to solve. Next, I'll be talking about nuclear equations, specifically balancing equations. So balancing nuclear equations is a crucial step in accurately representing nuclear reactions. Unlike chemical reactions where the number of atoms is conserved, nuclear reactions often involve changes in atomic nuclei. Balancing ensures that the total number of protons and neutrons on both mass and charge on both sides of the equation remains the same, maintaining the conservation of mass and charge. This process involves adjusting coefficients to achieve equality between the reactants and products, reflecting the precise rearrangement of nucleons during a nuclear reaction. Successful balancing provides a clearer understanding of the underlying physics and facilitates accurate predictions of the products formed in nuclear processes. Next, I'll be discussing the kinetics of radioactive delay and going deeper into that, half-life in radioactivity. So overall, kinetics of radioactive delay, I said decay. Delay in nuclear chemistry studies how fast radioactive substances break down over time. It looks at factors like nuclear structure and environmental conditions. Using terms like half-life and decay constants, scientists quantify this decay process. Understanding this helps in fields like medicine and the environment, contributing to progress in nuclear science overall. So when we discuss half-life and radioactivity specifically, so this concept pertains to the time it takes for half of the initial parent nuclides within a radioactive sample to undergo transformation into daughter nuclides. This principle draws an analogy to the concept of half-life in chemical reactions, reflecting to the temporal dynamics of radioactive decay. Mathematically expressed as T1/2 equals 0.693 over K, where T1/2 represents the half-life and K is the rate constant. This equation highlights the relationship between the duration of decay and the rate of transformation. So basically, in instances where decay transpires rapidly, results in a shorter half-life, a larger rate of constant is observed, rendering the substance more active. So conversely, a slower decay leading to a longer half-life corresponds to a smaller rate constant, indicating diminished activity of the radioactive material. Understanding these correlations enhances our comprehension of the nature of radioactive decay processes. And there is a checking for understanding. Please pause. And next, we'll be talking about fission and fusion. So firstly, I'll be discussing nuclear fission. And nuclear fission is the process where the nucleus of an atom splits into two smaller nuclei, releasing a significant amount of energy. This reaction is key in nuclear power plants where controlled fission is harnessed to generate electricity. The release of energy is accompanied by the emission of neutrons, contributing to a chain reaction. Nuclear fission plays a crucial role in both power generation and certain types of nuclear weapons. And for my historical example that I used in my research can be shown and more into depth in this slide, but it is basically on the Manhattan Project. And to sum it all up, this event just marked a pivotal moment in history as it demonstrated how we as people can harness nuclear fission for energy production. And it paved the way for further advancements in nuclear technology. For nuclear fusion, this is the process in which two atomic nuclei combine to form a larger nucleus, and it releases a substantial amount of energy. This is the same process that powers the sun. Unlike nuclear fission, which involves splitting the atoms, fusion actually brings atomic nuclei together. Scientists are exploring controlled nuclear fusion as potential clean and abundant energy source. And the historical example that I used for this in my research is in 1952, as the U.S. Conducted its first successful test of a hydrogen bomb. And this just also demonstrated the feasibility of controlled nuclear fusion reactions and as a potential future energy source. There is a checking for understanding, so please pause. And lastly, I just have some interesting facts. So one that I found really interesting was that bananas and the potassium-40 they contain actually, the potassium-40 is a radioactive isotope, meaning that eating bananas exposes you to a small amount of radiation, but it's completely harmless. The uranium in nuclear power plants is not the same as the highly enriched uranium used in atomic bombs. So basically, the uranium in nuclear power reactors is at a much lower concentration. And technetium is the first element that was artificially produced, and its name comes from the Greek word technetos, meaning artificial. And lastly, nuclear reactions in stars forge elements through nucleosynthesis. So basically, the elements that we have on Earth, including the carbon that's in our bodies, were created in the nuclear furnaces of stars billions of years ago, which I think is pretty cool. And that is all. Thank you for listening to my presentation, and I hope you enjoyed.